Swayam Prabha. Digital India. Educated India.
What we'll do today is do some examples for some of the fundamentals that we have learned in this course about the air pollution and air quality. The problem which you see on the screen is, I'll read that one and then proceed to do its solution. A moving diesel train discharges SO2 at the rate of 0.08 meter cube per kilometer, but the condition at which it is discharging, this one is the temperature of discharge, as you can see, is 1000 degrees Celsius and at 1 atmosphere. The emission gets distributed uniformly in the cross direction, that is 90 degree to the direction of train, in a triangular shape of size 20 meter height and 600 meter base, with train in the center. Okay, that now you can see a picture on the left hand side. So there is a train, okay, and you can see it's causing the emissions. As you can see, the black smoke coming out from the diesel, and this diesel, the smoke is dispersing in a triangular area which has a base of 600 meters and height of 20 meters, okay. And as the train is passing by a village, you can see a village stretching 1 kilometer along the railway track and at a distance of 300 meters. Obviously the half of this one is 300, so here is a village, okay, and the village length is, and you see the length of the village, as you see, is the 1000 meters. So whatever the emission that takes place from the diesel engine is completely dispersed in the area which I am redrawing for you. Okay, this is the triangular shape, and it is kind of dispersed through the entire area of the village. Fine. And what is the emission? Emission is 0.08 meter cube at 1000 degrees Celsius, 1 atmospheric pressure. Okay. Now let's see, a village stretching 1 kilometer along the railway track and at a distance of 300 meters from the track. So this is 300 meters from the track. So here is the, you can say, here are the, you can imagine like these are the people and their houses which are there, and this is the area where the people are there. Okay. And then and we need to attain an air maximum concentration of 200 microgram per meter cube. So in order for villagers to be safe, we want to maintain an air quality of 200 meter cube per 200 microgram per meter cube, and the condition for this meter cube is 20 degrees Celsius, 1 atmospheric pressure, and the averaging time is for 24 hours. Okay, and also note that the temperature drops from the center of the track at the rate 1 degree Celsius per 100 meter in the cross direction. So whatever it says, the temperature as we go away from the center, because obviously this little heat here, as you can see, as we go away from the center of the railway track, the temperature drops. Also note that the temperature drops from the center of the railway track at the rate 1 degree Celsius per 100 meters in the cross direction. Take the temperature at the center equals to 30 degrees. So what is saying is the temperature here, okay, is 30 degree Celsius, and as we go away from the center, the temperature drops at the rate of 1 degree Celsius per 100 meters. So you can very easily say the temperature at this point, or the temperature all along the village, okay, that's the temperature at this point will be, is dropping at the rate of 1 degree per 100 meter. So we are moving 300 meters, so 3 degrees Celsius will be dropped. So the temperature at this point, okay, let's really make it little solid, okay, and then let's call this temperature, obviously will be 27 degree Celsius. Okay, and we have to maintain an air quality for the people living in the village. Fine. Okay, so that's what the idea is. So now let's try to solve this one. So first of all, we know that the entire emissions that is taking place from the diesel engine is completely dispersed in this volume. Okay, as I draw this one. So first let's say volume in which it is dispersing. Okay, that we can very easily find out. The area of the triangle, that's 1 by 2. The height is how much? Is it 20 meters, and the base will be, the base is total 600 meters. Okay, and we have to find out the volume, and what is the depth is 1 kilometer or 1000 meters. So this is the area in meter cube in which all the pollutants will be dispersed. So let's find out this one, how much this comes out to be, and I have a calculator here. I'll try to calculate this one for you quickly. 20 into 600 into 1000, this much, and divide by 2 is something 6 into 10 to the power 6 meter cube. Okay, so we'll remember this number, that the air pollutants that is discharging from the diesel train will be completely be mixed in this area. Okay, now let's go to and try to find out what will be the mass of SO2 that is emitted. Okay, so what I'll do is I'll rub this one. Okay, or maybe we can go to the next space. Okay, so if you remember, what was the SO2 emission? Was 0.08 meter cube. What condition? 1000 degree Celsius and 1 atmospheric pressure. So let's change this, and this was per kilometer. Okay, and our length of the village also was 1 kilometer. So total emission that we got was from the train was this thing. So let's convert this meter cube first to the 0 degree Celsius. Okay, so then if you recall, we have the condition P1 V1 upon T1 equals to P2 V2 upon T2. Okay, and let's say I want to find the pressure is the same, so pressure strikes off. The volume here is 0.08, and what condition this volume is? 1000 degrees, so make it Kelvin. We add 273, and this is volume I want to find out. At what condition? I want to find out this volume at the 0 degree Celsius. So simply I can put here 273, and therefore I can find out the value of V2, and I'll do the calculation separately here. 0.08 times 273 goes to this much, divide by 1273, and this quantity comes out to be 0.0171 meter cube. Okay, this is the volume of SO2, volume of SO2, but remember at what condition? At 0 degree Celsius and 1 atmospheric pressure. Okay, fair enough. Now I want to convert this volume of SO2 in mass, and let's do that one. So how can I convert this volume into mass? Is, if you recall from the basic Avogadro principle, that 22.4 liters of gas, okay, let's write liter of the gas, is equal to 1 molecular weight, 1 gram, 1 mole, or I can say 1 gram molecular weight. So for SO2, 1 liter of SO2 will take how much of the mass? So SO2 molecular weight is 64 divided by 22.4 grams. Okay, that, and now this was for the 1 liter. So how much volume I have here? 0.017. So I can find out, I can also convert this into the liters, into 1000. This is liter, so this will give me how much mass? 64 by 22.4 multiplied by 0.017 171 into 1000. Okay, so this is what is the mass of SO2. I'll do the calculation for you. Into 1000 multiplied by 64 divided by 22.4. Okay, this came out to be about 49 grams of SO2. Okay, so what we have done the two steps so far. What we have done, we have found out the first the volume in which SO2 will disperse, that we did last time, and that came out to be, if you recall, 6 into 10 to the power 6 meter cube. Okay, and the second thing what we did was find the mass of SO2 that got emitted. Okay, that came out mass of SO2, and that we found out as the 49 grams. Okay, so you have the mass of SO2 and you have the volume in which it dispersed. You can find out the overall concentration of SO2 in the volume that in which the SO2 got dispersed. And don't forget that there is a village which is sitting in the same volume. So let's I'll try to remove this one and we'll write these numbers separately here. 6 into 10 to the power 6 meter cube, and mass 49 grams. I'll rub the whole thing. So what the next step for me would be to find out the overall concentration. So how do we find out the overall concentration? Then we can say, well, mass divided by the volume in which it is dispersed. So that will give me the concentration of SO2 in the region. So fair enough, SO2 concentration is this, mass is 49 grams. Okay, 49 gram divided by 6 into 10 to the power 6 meter cube. I can convert this microgram into this gram into micrograms, so that comes out to be, this will strike off. So I simply have 49 divided by 6 is the concentration per meter cube. Okay, all right, but let's this is not the final concentration. If you recall, our concentration is changing, okay, because the meter cube is changing. The 1 meter cube is different. If I can go back to the slide here, if you remember, you see here the 1 meter cube at this point and 1 meter cube at this point, they all are different because the temperature is changing. So this meter cube here, 1 meter cube here, and 1 meter cube here is just not the same. So okay, so I must change this meter cube to the conditions which are at the 27 degree Celsius. Okay, so let's find out that as to how we can do that. We can find this the concentration at 27 degree Celsius. Okay, so well, this meter cube, you should you change this meter cube, as you can see here, as the overall meter cube. So this meter cube will basically, what will happen, this meter cube will at the conditions 300 degree Celsius, at the 30 degree Celsius, or it will be different, and at 27 degree Celsius it will be different. Okay, so this, either we can convert this one or as approximately, because things will not change so much, so we can take the same concentration. So number of trains, okay, trains that can be allowed. Okay, what we need the concentration, required concentration is 200 microgram per meter cube. Okay, and one train, that 8.166 microgram per meter cube is contributed by one train. So 1 meter cube will be converted by 1 by 8.166. 166, and what I need is I'm allowed to contribute up to 200, so this will be 8.166 times 200. So this will become the number of trains that can be allowed to pass through the village. So I do 200 divided by 8.166, so that comes out to be what, 24.49 trains that can pass through here. Okay, but train has to be a full number, so the answer is that about 24 trains are allowed to pass through. The village. This is how a simple problem we can solve and try to find out as to how many trains can be allowed to pass through. Okay, so what we did is that we found out the overall SO2 concentration in the triangular area. But what we have to remember is that this meter cube, as you are seeing here, okay, it's really a function of temperature, and the temperature within the triangular shape or triangular prism, it is changing. So I must convert this to the required temperature where my standard is. So if you recall, and if I'll try to go back there, what was the standard that we wanted? 200 microgram per meter cube at 20 degrees Celsius. And what is my temperature here? 27 degrees Celsius. Okay, so this meter cube, really the point where I want to find out, this meter cube is at 27 degrees Celsius. Don't forget that. Okay, this is what I was trying to say here, is I'm trying to make a sign at for you, at 27 degrees Celsius, because the village temperature is 27 degrees Celsius, but our standard is at 20 degrees Celsius. So we must convert this concentration at the 20 degrees Celsius. So again what I'll do is that again follow the method V1 upon T1 equals to V2 upon T2. So V1 is what? V1 is my 1 meter cube, and what was the temperature here? 27 plus 273, and the volume which I want to find out is at what condition, because my standard is at 20 degrees Celsius. So let's write 20 plus 273. So my V2 equals to, so I'll do this one, 293 divided by 300. So that came out to be 0.9766. Okay, so this SO2 concentration is really 8.166 divided by, because my 1 meter cube is really 0.97 meter cube. Okay, 0.9766 meter cube. Okay, and this concentration becomes how much? I'll do the calculation for you, divided by 8.166. So that is becoming 8 point marginally change, 8.36 micrograms per meter cube is the concentration in the village at 20 degrees Celsius. Okay, so now I'll apply and I'll try to find out then how many trains can be allowed. So allowed concentration is 200 micrograms per meter cube. So number of trains, this is the contribution by one train. Let's not forget that. Okay, so number of trains allowed will be 200. That was my standard that I have to meet, and this was at 20 degrees Celsius, and the concentration caused by one train was 8.36 micrograms per meter cube. Okay, this also I got it converted to 20 degrees Celsius. See, it's very important that you convert both the things at 20 degrees Celsius. You see, otherwise this temperature here, as you see here, was at 27, and my standard was at 20 degrees Celsius. So it's very important that I convert everything to the 20 degrees Celsius. So then I divide this, and then let me see what the answer is. 200 divided by 8.36, and that comes out to be 23.92 trains that can be allowed to go through this one. Okay, so what answer came out to be? Number of trains, or diesel trains rather, that can pass through the village came out to be how much? 23.92. Okay, but then obviously the train has to be a full number, not the fraction. So actual answer should be 23 trains that should be allowed to pass through the village. It was an interesting problem. It involved some practical aspect of what we have learnt, and also apply some of the concept of simple conversion and applying some sense of emission to the air quality standards or air quality norms that we need to attain. So what we'll do is we'll move to the next problem now. Okay, you see the problem on your screen now, and then we'll try to understand this. And you have done this the background is already there. So what we're looking at, the question is, what will happen? Okay, I think I should write here, what will happen. Okay, when in a combustion process the CO level to CO level, if the ratio of O to C goes down. So first let's write, and then second thing, what happens to the CO level if the temperature goes up, and to NO if the ratio of N by O goes down, to ratio of NO by NO2 ratio with the temperature. But we'll do them slowly one by one. Okay, let's not worry about that. Let's do the first part, the A, and in A what we want to do the subsection 1. Okay, so basically what we should write is that we should write the equation CO2, and this is reversible equation, CO plus half O2. Okay, and don't forget that there is also energy will be on the other side. Okay, this is what is the reaction. So what will happen since it's a reversible reaction? So first, suppose I am simply saying, of course the mathematics we had developed, but also we can apply the common sense. If the oxygen O by C ratio is going down, okay, O by C ratio is going down, it means my oxygen content is becoming less and less. Okay, if my oxygen condition become less and less, then I am going to produce, because the combustion will not be complete, so my carbon monoxide will go up. Okay, so will rise. Okay, let's I'll do it once again for you, and so that there is no confusion about this. Okay, as you can see here, again let's write the reaction. In the combustion, what happens? CO2 can be the reversible reaction, it can be CO and oxygen, as you can see here. Okay, the question says O by C goes down, O by C goes down. O by C going down means oxygen is going down. Then oxygen is going down means this level is low. So then the reaction will be in this direction. Okay, so the reaction will be this way, we will produce more CO. Is that clear? Okay. Achha, now let's try to answer problem A, part 2. What will happen to CO if the temperature goes up? So if I say, okay, then we have to write the stoichiometry and the equilibrium constant. So if you recall from the earlier lecture, with the equilibrium constant here, it will be XCO. I'll explain you again what is the meaning of XCO, XO2 by XCO2. X are the mole fractions. Okay, So this I can write certainly the equilibrium from my chemistry background, and then this K equals to, as you will recall, is 3 into 10 to the power 4 exponential minus 6700 by RT. Okay. If you see this one, if the temperature goes up, okay, now I saying temperature goes up, what will happen to CO? Will it go down or it will go up? It will certainly go up, because we can see from here that if the K, as my temperature increases, okay, the K value will go up, and so will be the CO value. That's very clear. So what we have answered, that in combustion process, if we are decreasing the oxygen content, okay, then the CO level will go up, and also we are increasing the temperature in the combustion process, the CO level will also go up. Okay, that you can very clearly see. So now what we'll do is we'll take the, so now we have done A part 1 and part 2, so let's go to part 3 now. Okay, so now we have section for question A subsection. Let's do the part 3. So the question is, what will happen to NO, okay, if N by O ratio goes down? Okay, if my N by ratio is going down, it means what is happening? If N by O ratio, it means I am putting more oxygen, putting more oxygen, and we all know if there is a excess oxygen in combustion, more NO is formed. And recall that what was that NO used to be? We used to call it thermal NO, okay, or the thermal NOx. So the answer is, if this ratio is going down, means NO is going up. So answer is NO. Under this condition, NO will rise. Okay. Now let's do the part 4 of the section A. I'll again remove this A and part 4. Okay, this is a little interesting, because now it involves both NO and NO2. Okay, it says what will happen to the ratio of NO to NO2 ratio with temperature. As the temperature is rising, what will happen to NO and NO2? So for this we'll have to slightly write some equations, and that I'll do here for you. If you recall, for this one, that what was the formation? That was producing NO. Let me write this as the equation 1, and this is this NO which can further convert into NO2. And let's write this as the equation or reaction 2. Okay, so what I'll do is that I'll write separately the equilibrium constant for equation 1 and equation 2. So suppose the equilibrium constant for this one is K1 and for this one is K2. So what I can write, that K1, or what I am interested in really, is the ratio of NO to NO2. So I can write the equilibrium reaction in the form of the NO and NO2 from equation using 1 and 2. So I can write the mole fraction of NO, okay, will be equal to, from reaction 1, K1 times XN2 1 by 2 to the power 1 by 2 XO2, okay, to the power 1 by 2. Well, I'm sure everyone can write that. I'm just using this equilibrium constant and trying to write the what will be the mole fraction of NO. So similarly, I can write the mole fraction of NO2 using equation 2, but this time both the constants will be involved, because reaction 2 depends on reaction 1. So I can write xNO2 is a K1 times K2 xN2 power half and xO2. Okay, here. Okay, let's try to this is what is the thing that will come. So now what I need to do is I want to find the ratio NO by NO2. So I can find out the ratio xNO by xNO2. Okay, K1 will cancel. Okay, and this will cancel, and then I'll have the 1 by K2 times xO2 1 by 2. Okay, and this K is a function of temperature. Okay, what happens, all you can recall is as the temperature goes up, the temperature goes up, so the K will go up. We all know from the basic chemistry that the K will go up. I'm sorry, this K2 will go up. So if the K2 goes up with temperature, what will happen to this ratio? This ratio will decrease. Okay, I can try to give you the value of K2 if you like. K2 equals to 2.5 10 to the power minus 4 times exponential minus 13720 by RT. Okay, so the temperature will, as the temperature will go up, the value of K2 will also go up. If the K2 goes up, okay, the ratio will come down. So let's we haven't written the final answer, so let's write the final answer here. Okay, when the T is going up, okay, K2 is going up, K2 is going up means this ratio is coming down. So with rise in temperature, the ratio of NO by NO2 will come down. Okay, is that clear? Okay, that sounds good. So let's go to the next problem now. Okay, we'll do another problem. Okay, and this is problem about the internal combustion engine. And then oh no, I think we need to answer something else before we do this. There's a B part also of the problem. We kind of didn't look at the B part. Okay, so let's write the B part also. So we'll rub this. Now the B part says, let's make it B here. B, it's in the ambient air. Okay, now this was inside the process, combustion process in the ambient air. To ozone level, if hydrocarbon to NOx ratio goes down in VOC limiting region of ECMA model. Okay, so if you recall ECMA model and the results of ECMA, I can do it again. Okay, what was here? We had the hydrocarbons on this scale and NOx onto this side. Okay, and we had plotted the levels of maximum ozone concentrations. Okay, something like this. So it was like maximum, and then the concentration will reduce in this direction. Okay, so once we have this ECMA, so now let's try to answer question 1. To the ozone level, these are all of the ozone levels. Don't forget this is, these are, what are these? Ozone iso concentration lines. of maximum concentration. Okay, and then as you see, we go this direction, it will reduce. Okay, so let's look at the problem. To ozone level, if hydrocarbon to NOx ratio goes down in VOC limiting area. Which was the VOC? VOC means, let's understand, VOC is the same as hydrocarbons. Okay, it's the same as hydrocarbon. Let's not confuse about this. So which area is VOC limiting area? This region. Okay, this region. Okay, why VOC limiting? Because here I have a high level of NOx. Okay, and the VOC is low. We can even draw one more picture. So let's remove this. Okay, let's make one more if you like. And my this area is my limiting region of VOC limiting, because here VOC is very low, and as I move this direction, as I am going this direction, my hydrocarbon is increasing. So this is the area. So now the question is to HC to SC NOx. Okay, SC NOx, what is happening to this one? It is going down. Okay, how can it go down? Okay, I can either reduce NOx, okay, or I can increase NOx. So I'm increasing the NOx. Okay, it has to go down, so I can increase the NOx. So it means if I'm increasing, then I'm moving in this direction. Okay, as I move in this direction, my ozone levels are dropping, because this is the maximum ozone concentration. Then smaller, then smaller, then smaller, then smaller. Okay, so by increasing the NOx, I'll reduce the ozone level. Okay, somebody can argue, well, I can reduce this ratio by decreasing hydrocarbon. Let's consider that also. So okay, at least we understand, if we are decreasing this ratio, my ozone level is also decreasing. Okay, why decreasing? I repeat, this in order for this ratio to go down, my NOx must increase, and I'm increasing the NOx. Okay, as you can see, I'm going from down to up, or down to up, as you can see, and my ozone level is going down, and I put the down arrow here. I can also decrease this ratio by decreasing the hydrocarbon. So let's see if I can remove this. Okay, how can I go by? I can decrease this ratio by decreasing the hydrocarbon, means again I am moving in this direction. Okay, so if I move in this direction, what is happening? Again my ozone concentration is dropping. So I can conclude that as this ratio goes down, my ozone level will also go down. So answer is ozone level will go down with the ratio SC NOx goes down. Okay, that is what is the answer that I will give to problem B, section 1. So we answered this one. Okay, let's quickly also answer the next part. Okay, I'll reduce. So what I'll do is I'll remove this. That is fine. Let's remove. Okay, still looking at this ECMA model. Then say the question is, what will happen to ozone level in hydrocarbon saturation region of ECMA model with reduction in hydrocarbon? Okay, so it's we have to again look at this figure. Okay, I'm reducing the hydrocarbons. You see, I'm moving in this direction. I'm reducing the hydrocarbon. I'm moving in this direction. I'm reducing this hydrocarbon. And what is happening to the ozone? Ozone more or less remain constant. Why remain constant? You can see, because these lines, as you can see them, they essentially appears to be, and it is parallel to my x-axis on which I have plotted hydrocarbon. So the answer is for part 2, there will be no change. When I say no change, means really no significant change. No change in ozone concentration by reducing hydrocarbon in hydrocarbon saturation zone. Okay, you see here, this is the key part in the hydrocarbon saturation region. So you can see this is the region, lots of hydrocarbon. Okay, and then even if I in this region, okay, if I can take this window, even in this region I am reducing the hydrocarbon, moving from right to left, as you can see, but there is no change in the ozone. It's funny, but this is true. Okay, let's go to the next problem, because we are all doing the problems today. Okay, now we are moving to the internal combustion engine. The problem is, an internal combustion engine is using a kind of fuel called isooctane, that is C8H18, under precise stoichiometric conditions. You understand that. Determine the percentage of CO2 in the exhaust. That's a question, or the part 1. And it also says, if the combustion process became upset and 100 ppm of isooctane escaped unburnt, then what will be the CO2 percentage in exhaust on dry and wet basis. So we will do this one. So in order to do this one, we have to invoke the combustion fundamentals of combustion engineering. Okay, let's draw a line here, and if you will recall that any hydrocarbon fuel which has a carbon and hydrogen, okay, if it burns, I'll quickly write the balanced equation for you. Oxygen plus, don't forget the nitrogen that comes in, and this gives rise to your x moles of CO2 plus y by 2 moles of water plus 3.76 x plus y by 4 moles of nitrogen. That's a complete combustion under the stoichiometry. So if you recall, if you say for 1 mole, let's not forget that here it is just 1 mole. So what are the reactants for 1 mole? Let's call that reactants R. This we have done before, but I'll do it again for you. The reactants, or let's call this reactant really, as I used last time, I must use the same thing, is the F. How many moles? This plus this, so I can say 4.76 x plus y by 4 moles. Okay, they are the reactants. And look at the products. I can also write the moles of the products. Products are on my this side. So x mole of CO2, agreed, y by 2 moles of H2O plus 3.76 the total moles on my product side. Okay, so the percentage CO2 in exhaust, how many moles are there CO2? X divided by the total moles that I have here, okay, in the exhaust. So that is nothing but, or if I want to find out, I can find out this one right here. So what is my value of X? X equals to 8 and Y equals to 18. Okay, so I can find out the moles. So X is nothing but 8. So let's write 8 plus Y by 2, Y is 18, so that's 9 plus 3.76 x plus y by 4. X is what? 8 plus y is 18 by 4. Okay, and this came out to be 8 by 64. So that is 12.5% of CO2 in exhaust. That is my answer to this problem. Determine the percentage CO2 in the exhaust. Okay, I repeat, I wrote the general combustion equation, reaction equation, balanced it, and then find out the product side. Product is x moles of CO2, let's not forget x moles of CO2, y by 2 moles of water, 3.76 x plus y by 4 moles of nitrogen. So I could find out the total moles because my x, y are known. X is equals to 8, y is equals to 18, so I can find out the product, and the moles in the exhaust of CO2 is x divided by the total moles, so that is 8 by 64, then that's get you 12.5%. Okay, and this is what generally you will find, that the CO2 concentration is generally around 12% in normal combustion process. Well, it can vary, but that's the general value. Okay. Okay, suppose the products I am calling them as M. Okay, then you recall we gave a formula to you that ppm of unburnt hydrocarbon was F. Okay, and I'll explain you what is F. M minus F times M plus F times capital F. Okay, what is F? F is the fraction of hydrocarbon escaped unburned. Okay, all right. So what how much ppm of unburned hydrocarbon in the exhaust? I've been given as 100 ppm. So I can put this equals to 100. Okay, and then I can find out what will be what is unknown to me. My F is already known to me. Okay, my M is already known to me, and what is unknown is I can find out the F. So I'll not do the calculations here, but if you run through this calculation, the value of F will be equal to 0.0064 mole fraction of Ci8H18 that got escaped. Okay, so this is one thing, I got this one. So now what I want to do is, again I want to find out the CO2 in the exhaust. So I'll remove this. Okay, and we'll use this information. Okay, so when something is escaping unburned, so my CO2 will be less. Okay, so CO2 under the condition something is going unburned, CO2 will be my equals to CO2 will be my X minus Fx. So that is 8 moles of CO2 minus 8 into 0.0064. So that will be equal to 7.948 moles of CO2. Okay, now moles of products. That will be equal to, that will be M times 0.0064 of M plus 64 of 59.5. Okay, and my M was the the total product when everything got completely burnt, but this time it is not completely burnt because something is escaping. So if you recall, what was my moles? M was 64 minus 0.0064 times 64, and this is the portion which is showing up in the exhaust, so I'll just simply add this one up, and this is the portion that is coming out from the reactant side, where reactant completely did not convert into CO2 and hydrocarbons, so those portion of the reactant will come up as such. So this becomes 0.38. okay, the whole thing comes out to be 63.977 and approximately 64. So the percentage CO2, okay, CO2 remains nearly the same, or there will be slight change actually, because what you have to do really now is that answer will be 7.948 divided by 63.977, and that came out to be, I can show you that number, 7.948 divided by 63.77, that came out to be 12.46, almost the same as the last time. Okay, and now another part of the question says that exhaust on dry basis. Okay, so this was the wet basis because we had considered the moisture. If you don't consider the moisture, then what will be the value? So I can remove this now. So I will not consider the moisture, and I can find out on the dry basis. Okay, so in the exhaust, CO2 is the same, 7.948. okay, and total was 64. Okay, minus the moles of water. Okay, how much moles of the water will be? Y by 2, Y was 18, Y 2 is 9, so that thing comes out to be around 14.44 percentage. That is CO2 in exhaust on dry basis. What is the difference that we have done? We are not considering the water, okay, and that has the 9 moles. Where is the 9 moles coming from? Y by 2. Y, what is Y? Y is 18. 18 by 2 is 9. So in the exhaust, we are not considering the moles of water. So it means whatever the concentration, that will be on the dry basis. Sometimes we, as air pollution engineers, we need to report something on the dry basis, so that you learn from this this example that we can report the CO2 concentration on the wet basis and the dry basis, and also under the condition when some part of the hydrocarbon got escaped unburnt. So that is another example that we have done. So what we'll do is that we'll do one more example of different kind. Okay, the question problem 4 that we are doing is examine the particle size data given in table 1, and I'll show you table 1 in a moment. Plot the data on the log probability plot as in the figure 1, that also will give you the figure 1, and then answer the following question: is the particle size distributed log normally? What is the mass median diameter of the particle, and what is the geometric standard deviation of particle mass distribution? This information we require a lot in terms of looking at the particle size distribution in the ambient air. So what we'll do is go to the next one. Okay, here is the data which is given to you in the table 1. So what the people have done, something what we do the sieve analysis for that matter, that this is the range of the particles Okay, and what was the concentration in this particular range, as you can see, and the mass in the range, how much was the mass, that you can see, and this is the cumulative mass. So the between the particle size, let's say 2 and 4, the minimum diameter was 2. Okay, the concentration in the particle size range 2 to 4 was 14.5. Okay, and the mass size of the particle in this size range was 7.25, as it was the percentage mass. So the cumulative mass was 0.5. Okay, and then what you can do is that you can, all the cumulative mass are shown here, that will increase and finally should add up to 100. Okay, and then so what we have to do, the plot onto the whole thing on the log probability plot, because why you want to say, you want to find out if the distribution of the particle size is log normally distributed. Okay, so what we have done here on this side, we have plotted dPa, the particle size, or this column. Okay, and this side we have plotted cumulative, no, I'm sorry, we have, this is the other way around we have done. This side we have plotted the particle size, that is my dPa, and this side plotted cumulative mass, which is this column. Okay, and now let's plot this one. For example, see here the dPa is 2, this value is 2, so let's go 2, and what is the cumulative mass? 0.5. so I go from 0.5 and plot this point at this dot. Let's go to second point, 4, so let's say 4, and at 4 it is the cumulative mass 7.75. so this is 2, 5, 7.75 will be somewhere here. Okay, then go and plot the point, let's say 6. Okay, then you go 6 here, then for 6 I have the cumulative mass as 20.1, so this is 20.1, and then I am plotting this as 7. Okay, and finally let's plot the this condition here is 20, for 20 diameter is 20, so we go on 20, and how much is the mass? Is 84.13. so this is something like 80 and 84.13, so it comes here. So when I join this line, I'll get a straight line more or less. Okay, so this is what is my log plot. So since it is coming straight line, I can certainly say that this is the data, or the particle size is log normally distributed, and I want to find out the median diameter or the mean diameter. So I should go the cumulative value equals to 50. So I go, this is my 50 point, you probably can see this is 50, then I go here on 50 line and go this side, and I can find out my mean diameter. So you can say D50, or the mass median particle diameter, is 10 micron. So cumulative is 50, then I can go here this. I have to find out the geometric standard deviation. So this is the relationship as we discussed in the class, D50 by D15.78. So this is D50 value is how much? 10, that we just now we got this value 10, and at D15.78, so I have to go 10 and between here, so I have to go here and then plot here 15.78 and then get the value somewhere here. That is something like close to 5, as you can see here. This is 5, and then I can take this value 5, and then I can find out the standard deviation, the geometric standard deviation as 20. You can do on the other side also. You can take D50 and or 84.13. If I take 84.13, that also will give me the same thing. So this is 80 here, as you can see this point is 90. So in between, and this you are getting answer 20. You can see here 20. So I can take the 20 here, 20 by 10, that will still give me the same answer. So you can see here that what we have done is we had the data and we could say the particle size distribution was log normally distributed, and the mean the mass median particle diameter was 2 micron, I should say here 10 micron, sorry, as you can see here, and the geometric standard deviation was 2. Okay,